Okay, hello everyone. So today I'm going to discuss a problem from the last year Canadian Mathematical Olympiad. So the year 2017, and it was problem number 4. It's a geometry problem, and I would say that it's a difficult one. So the problem is stated as follows. Points P and Q lie inside parallelogram ABCD and are such that triangles ABP and BCQ are equilateral. Prove that the line through P perpendicular to DP and the line through Q perpendicular to DQ meet on the altitude from B in triangle ABC. So let's look at the picture, how it looks like. So the picture is the following, and so basically we have two equilateral triangles. So we have a parallelogram ABCD, and on two sides of this parallelogram AB and BC we have two equilateral triangles. So we have like two additional points P and Q, the vertices of these equilateral triangles. And so then we construct two additional lines, a line through P perpendicular to PD, so here on the picture it's PH, and the line QH perpendicular to DQ, so they meet in point H. So we need to prove that this point H lies on the altitude from B to AC, or, which is the same, we need to prove that BH is perpendicular to AC. So this is the problem setting, and so if you want to try to solve this problem on your own, you can stop the video and return to it later to discover the solution. So now we are going to discuss the solution to this problem. So as I said, this problem is not very easy. I consider it not very easy, and so the solution will be divided into 4 steps. The first step, in the first step we are going to prove that triangle PDQ is equilateral. So basically what we see on the picture. So let's consider first the rotation by 60 degrees around point A. So in this rotation, when we rotate around point A by 60 degrees, we see that point P goes to B. This is very clear, because ABP is an equilateral triangle. So when we rotate around, equilateral triangle means that all its sides are equal and all its angles are equal to 60 degrees, right? So if we rotate around one of the vertices of this triangle, the other vertex goes to the third one. So P goes to B when we rotate around A by 60 degrees. So then let's see where the point D goes under this rotation. So point D goes actually to the point Q prime, which is the vertex of another equilateral triangle constructed on the side AD of the parallelogram. So basically we introduce another equilateral triangle ADQ, which is constructed on the side AD. So in the problem setting we had the equilateral triangle BCQ on the side BC. but now we consider kind of the symmetrical to it equilateral triangle Q prime, and so they're symmetrical around the center of the parallelogram, across the center of the parallelogram. So so we see that point D goes to Q prime. Okay, so now we are going to consider another transformation of the plane, namely the point reflection across O, across the center of the parallelogram. And under this point reflection, we see that B of course goes to D, so the one of the vertex of the parallelogram goes to the opposite vertex, and then Q prime goes to Q, because the triangle ADQ prime is symmetrical to BCQ. They're symmetrical to each other across point O, therefore like Q prime goes to Q. So now we see that if we combine these two transformations of the plane, then the point P goes first to B and then to D. So in total P goes to D, and then point D first goes to Q prime and then goes to Q. So in total we have D goes to Q, right? So PD goes to DQ. So P goes to D, D goes to Q, so then PD goes to DQ. So, but what does it mean? Like, we see that the combination of two transformations of first we rotate the plane and then we consider point reflection. So the superposition of these two transformations is also some kind of transformation, and so like the segment PD. So first we know that this transformation preserves the length, because when we rotate around some point by some degree, a segment always goes to an equal segment. The rotation always preserves the length, but the second transformation, point reflection across a point, also preserves the length, right? So it means that if we establish that one segment goes to another, then these two segments are equal. Their length is equal. So therefore PD is equal to DQ. But also we know that we can establish the angle between these two segments, like between these two lines, between PD and line PD and line DQ, because when first we rotated by 60 degrees and then we made point reflection. So after the rotation, like the line PD was rotated by 60 degrees and then point reflection, but point reflection, under point reflection a line always goes to a parallel line, right? So after the first rotation the line PD goes to some line rotated by 60 degrees and then it goes to a parallel line. Therefore, like under the combination of under the superposition of these two transformation of the plane, the line PD goes to some line, goes to the line DQ, which must be under the angle 60 degree from the original line, from PD. So therefore the angle PDQ is equal to 60 degrees. So that's what we conclude from these two transformations. So now we see that we have the triangle PDQ, and in this triangle we have a pair of sides which are equal to each other, and we have the angle between these two equal sides is equal to 60 degrees, but this immediately implies that this triangle PDQ is equilateral, right? So that concludes the first step. That's what we wanted to prove in the first step, that the triangle PDQ is equilateral. Okay, so then we are going to introduce two additional points, K and N. So the point K is the intersection point of the lines BQ and AD, like on the picture. And N is the intersection of the lines BP and CD. So now we are going to prove that these, like we're going to prove something about these 2 points. So let us notice that the angle QKD is equal to the angle QBC because the sides BC and AD are parallel to each other. Because in the parallelogram ABCD, the opposite sides are parallel, and therefore the angles are equal. QKD is equal to QBC, but QBC is equal to 60 degrees because the triangle BCQ is equilateral, right? So, but also what we know from the previous step, from step 1, is that the triangle PDQ is equilateral, and therefore the angle QPD is also equal to 60 degrees, right? So from this, basically, we conclude that the angle QKD is equal to the angle QPD. Now, because these two angles are equal, we conclude that the 4 points K, P, D, and Q, they all lie on the same circle. Basically, this quadrilateral K, P, D, Q is inscribed or cyclic. Or, like, to state the same thing in another manner, like if you consider the circumcircle omega of the triangle PDQ, then the line K lies on this circle omega. Okay, so now we are going to prove basically a very similar thing about the point N. So we see that the angle PND is equal to the angle NBA because AB is parallel to CD. Because the opposite sides AB and CD are parallel, therefore the angle PND is equal to NBA. But NBA is equal to 60 degrees because ABP is an equilateral triangle. Therefore, but also from step 1 we know that PDQ is equilateral. Therefore, the angle PQD is also 60 degrees. Therefore, the angle PND is equal to the angle PQD. Since these angles are equal, we conclude that N lies on the same circle, on the circle omega, the circumcircle of triangle PDQ. So like these two angles subsect the same arc in this circle, the arc PD. So basically in this step we proved that these two additional points that we introduced, K and N, so we introduced these 2 points and we proved that they lie on circle omega, on the circumcircle of triangle PDQ, which is, by the way, an equilateral triangle which we proved in step 1. So this concludes step 2 of the solution. So now we are going to step 3. So in step 3 we first let's establish some the equality of some angles. So we see that the angle AKB is equal to the angle KBC. This is because the sides BC and AD, the opposite sides in the parallelogram, are parallel to each other. So BC is parallel to AD, therefore the angle AKB is equal to angle KBC. And it's equal to 60 degrees because KBC is equal to 60 degrees because BCQ is equilateral. So then it's equal to ABP because it's also 60 degrees. ABP is an angle in the equilateral triangle ABP. But then angle ABP is equal to BNC because of the parallelogram, because of the parallelism of AB and CD, because AB is parallel to CD, the opposite sides in the parallelogram, therefore ABP is equal to BNC. So in total, we look at the beginning of this chain of equalities and at the end. So the angle AKB is equal to BNC. AKB is equal to BNC. Okay. So then the angle BAK is equal to the angle BCN, just because they're opposite angles in the parallelogram ABCD. So we have these two pairs of angles which are equal to each other. Therefore, we conclude that these two triangles KAB and NCB are similar, like the triangles that are shown in green on the picture. They are similar to each other because they have two pairs of equal angles. So because they are similar, we can conclude that the proportion of their sides is also equal to each other. Therefore, AK over AB is equal to CN over BC. So this is the proportion of the corresponding sides in the similar triangles. So then we can just the manipulation of this equality. So we conclude that AB multiplied by CN is equal to AK multiplied by BC. But then we can replace AB, we can replace it with CD, because AB and CD are two opposite sides in the parallelogram ABCD, therefore they are equal. So AB is equal to CD. Therefore, in this equality, we can replace AB with an equal segment CD. And on the right, we similarly replace BC with AD. BC and AD are the other two opposite sides in the parallelogram. Therefore, they're equal, and we can replace BC with AD. So therefore, we obtain this equality. CD multiplied by CN is equal to AK multiplied by AD. So now that is interesting. So what does that mean? That means that the points C and A have the same power with respect to omega. So why is that? So remember, from step 2 we concluded that we know from step 2 that the points K and N lie on omega, on this circle, like the circumcircle of triangle PDQ. So with respect to this circle omega, what is the power of point C? It's like we have line CN, which crosses the circle omega in 2 points, D and N. So we know that the power of a point with respect to a circle is equal to like when the line crosses a circle in 2 points, like the power is equal to the distance from this point to the first point of intersection multiplied by the distance to the second point of intersection. So basically the power of the point C with respect to omega is equal to CD multiplied by Cn. And this, by the way, does not depend on the line. So, and the point, the power of the point A with respect to this circle omega is equal to AK multiplied by AD. Therefore, these 2 points A and C have the same power with respect to omega. But if they have the same power, then we can conclude that they have the same distance to the center of the circle, because what is the power of the circle, the power of a point with respect to a circle? Like, it's also equal to the tangent squared, which is the same as the difference between the distance to the center squared minus the radius squared of the circle. The radius is obviously the same, and therefore, like, the C O prime must be equal to A O prime. Okay, so that's how we conclude that C O prime is equal to A O prime. So basically, that the center of this circle omega lies at the same distance, has the same distance to points A and C. So this is the main conclusion of this step. This is like, now we are actually very close to the solving the whole problem. So now let's move to the fourth and last step. So what we see here is that, so we proved in step 3, in the previous step, that C O prime is equal to A O prime. But then we see that O, the point O, like the center of the parallelogram, divides the diagonal AC in half. So basically, it means that in triangle A O prime C, O prime O is a median. But then because these two sides A O prime and C O prime of this triangle are equal to each other, therefore this median is also an altitude, right? So O prime, then we conclude that O prime O is perpendicular to AC. O prime O is perpendicular to AC. So then let's see some other things. So now let's recall that we had this point H in the original setting of the problem. So this point H was constructed as follows. So we had a line through P perpendicular to PD, and a line through Q perpendicular to DQ, and then these two lines meet at H. So, but like, we see that because this angle HPD is a right angle, like it's 90 degrees, therefore HD is a diameter, right? So HD is a diameter in this circle, and by the way, H also belongs also lies on this circle omega, because like in the quadrilateral HPDQ we have like two opposite angles are equal to 90 degrees, therefore like its sum is equal to 180 degrees, therefore like it's a inscribed quadrilateral or cyclic quadrilateral, therefore H lies on omega. And it's not just that it lies on omega, but it's HD is the diameter of this circle. Therefore, its center O prime lies on this line on HD, and it's like it divides this segment HD in half. So O prime is a midpoint of HD, right? So now we see that we consider the triangle HDB. Okay, so in this triangle we have like the point O prime is the midpoint of the side HD, and the point O is the midpoint of the side BD, and therefore like O prime O is a mid segment in this triangle. O prime O is a mid segment in triangle HDB, right? But it means like it immediately implies that because like a mid segment in a triangle is parallel to its side, therefore we conclude that O prime O is parallel to BH. But like we already proved that O prime O is perpendicular to AC. Like this is the first line on this slide on top. So we have two parallel lines, O prime O and BH. One of them, O prime O, is perpendicular to AC, but then we conclude that the other one, BH, is also perpendicular to AC, right? So BH is perpendicular to AC. This is exactly what we needed to prove, and so this concludes the whole solution. So it was kind of a long video, but I hope you enjoyed it. So okay, goodbye.